I will say something about computing with Millett-Ewing notation. Okay. So, and I will provide some context about where this notation occurs and how it is being used. So I have given some talk some time ago about how to use Knotscape. Okay, so Knotscape is a program that was developed by Hosty and Thistlethwaite to provide access to knot tables and then also to compute some invariants. So for the purpose of this talk, it's not very important to know exactly what it does, okay, and how it functions, but the Millett-Ewing notation also appears inside this Knotscape. So anyway, so Knotscape has, so let's say I write a box for some kind of an object that occurs, and I write an arrow with a label on the arrow to say what is the tool that transforms between different objects. So anyway, so in Knotscape, there is a main window, which allows you to work with Dowker-Thistlethwaite notation. So DT, so this is called Dowker-Thistlethwaite. And my previous talk explains how this notation is built, and this is a notation that can be used to describe knot diagrams. So this is a notation for knot diagrams. It has a certain sequence of signed even integers, not very relevant to recall this now, what exactly it does. You can find this in the recording of my previous talk. Okay, so there is a Dowker-Thistlethwaite notation of knot diagrams. Okay, and you can load, so you can load this in, or you can input this into the text window. So you can load tables. You can also input it by hand. So I mean, you have these notations, and from this notation, the program computes several things. So one thing that this does is, or let's say, so it can compute link polynomials. So there are these polynomials like the Homefly polynomial. So this is something that whenever you have a link, you can associate to it a polynomial. In this case, it has two variables, and this polynomial satisfies, if we do this depending on a convention, let's say it satisfies the rule Z inverse of P of a positive crossing minus Z V. Minus V of the P of the negative crossings is equal to ZP of the smoothed out crossing. Okay. So which means when you have three links with diagrams which are equal, except at one place where the one is this way, the other one is the other one, and the third is the third way, then their polynomials are related by this relation, and you can use this to explicitly compute the polynomial. So this is also the Homefly polynomial, sometimes called Homefly PT. So this is a polynomial that goes from links to some ring of polynomials in variables, depending on how you call them, let's say V and Z. And I emphasize that you can have negative powers. So obviously here you see that you get negative powers. So there can be negative powers on the variables. And in these links are oriented. And just historically, so the name Homefly stands, this is an acronym of the discoverers of this polynomial. So it was discovered simultaneously by these 6 people and then also independently by these 2 a little bit later. Okay, so so for example, the Knotscape is managed by Hosty and Thistlethwaite. Okay, and Hosty, okay, is one of the discoverers of that. So this is the H here, the same person. Okay, so anyway, so so you can use so you can compute from this Humphrey polynomial. You can also compute Kaufman. Maybe just for reference, in this article that I have made available on the system, where Millett and Ewing discuss this, their algorithms, this polynomial, they call this the oriented polynomial. And this one, they call this the semi-oriented. So you can compute this and then just you can use this. So this is the Humphrey polynomial usually carries the letter P, and the Kaufman polynomial usually carries the letter F. Okay, this is how these polynomials are being used. And from here you can by substitution you can get the Jones and the Alexander. Not me, okay? I think I thought many times this is somebody whose family name was Alexander and who lived 100 years ago. So this is so, and so you can do some variable substitution to guess, and these are polynomials in one variable. Okay. Okay. I need this later, so it's better to keep it. So anyway, so you can use Knotscape to compute polynomials when you have this Dowker-Thistlethwaite notation. But what this really does is it converts the Dowker-Thistlethwaite notation into the Millett-Ewing notation, which is the main object that I'm going to talk about. And then from there it uses, okay, from there it uses this tool, so the Millett-Ewing. So it uses the Millett-Ewing code to calculate these polynomials. So the Humphrey and the Kaufman polynomial, there are 2 separate programs for this. So one is for this, one is for that. So these are essentially adapted from Millett-Ewing's original programs that were used. Okay, and then so Millett-Ewing did not have this and that, but this is kind of, so this was a front end which was added by Thistlethwaite. So this is Thistlethwaite. So he added some extra, a piece of code to the Millett-Ewing program, so to perform this substitution, so that when you want to calculate the Jones polynomial, then you get the Jones polynomial. But the calculation really goes over the Humphrey. So it calculates the Humphrey and then it substitutes. Okay. So in fact, you can, so this is well known, that you can get the Jones also from here. So the Jones is also a special case of the Kaufman polynomial, but this is not efficient to compute this way. So if you want to calculate the Jones polynomial, via the Humphrey polynomial is much faster. So this is what this is. If you check out the Knotscape, then this is essentially what it will do. Although of course you do not see this step. Okay, this step is kind of internal. So there is a tool which is called mbt_can.c. which is part of this this whole package. And what this does is it converts the Dowker-Thistlethwaite notation to the Millett-Ewing notation, where so MBT stands for Morwen B Thistlethwaite. I mean, my name is long enough, but okay, with Thistlethwaite's name, I have even more problems. So anyway, so MBT stands for Thistlethwaite, and Ken is Millett. So this is where this the name of this tool comes from. Okay, I mean, of course, you do not see this, but I explained that this is being done in order to provide the context for the use of the Millett-Ewing notation in the Knotscape. Okay, so this notation was invented by Millett and Ewing in order to write code for calculating the link polynomials that can also be used in Knotscape. Okay, so and now I should so there are a few more things. I think I said this also when I talked about Knotscape, but Knotscape has other functionalities. So it has a link editor, which is called Linksmith. So where you can draw with your mouse a link as a polygon, okay, with straight lines. Okay. And so you can if it is a knot. So if this is a knot, then you can get a Dowker-Thistlethwaite notation out of that. Okay, so you can get a Dowker-Thistlethwaite notation, but this editor also allows you to draw, for example, links. So this is not restricted to knots, so you can draw also links with this. But unfortunately, you cannot use links to get Dowker-Thistlethwaite notation because this only works for knots. But then I wrote myself my own. Okay, so I wrote myself my own code. Let's say when I put a star. So this is my stuff. Okay, I wrote myself a code that if you have so a Linksmith diagram, then you can get Dowker-Thistlethwaite Millett-Ewing notation from that. So and I use this. So this works also for links. Okay. This is very useful because I want to make so I can compute link polynomials also for links with multiple components using this by bypassing this Dowker-Thistlethwaite notation restriction. Okay, so I can do this also for links, and this same code. For instance, I can use to create, EPS files. So which I use then in my paper. So many of these the pictures in my papers are generated with my own tool that uses Linksmith to generate EPS files. So that can be used for images. And then you need to adjust a little bit here, and then you can. But so anyway, we can return to the Millett-Ewing notation. So Millett-Ewing notation was used primarily originally for this polynomial computation thing. But then there are some other things in Knotscape. For example, it has some hyperbolic stuff. So hyperbolic invariance. Okay. That can be computed. So there is a tool that you can compute hyperbolic invariance from the Dowker-Thistlethwaite notation. So this means you get some. So you input some knot with Dowker-Thistlethwaite notation, and you can get some mostly most importantly. Well, so you can compute volume, and then some other things which I'm not that familiar with. Anyway, so you can do this as well. And the interesting thing is, so this is code written by Jeff Weeks. So this was the third author of this article in the Math Intelligence, so that explains the Hauspeth-Isseltweit program. Okay, so he originally wrote it for his own program, but it was adapted so that you can get also some hyperbolic invariance from the Hauspeth-Isseltweit notation. But interestingly, actually, some of these packages seem to be working with the Millett-Ewing notation. So inside in this Jeff Weeks package, there seems to be some support for the Millett-Ewing notation that works for links. And then I remember some time ago, I was wallowing in the code and I was able to twinkle with it so that I can get at least the volume computable from the Millett-Ewing notation, which is very useful because Millett-Ewing notation, so I should emphasize, this is, okay, this is a notation for links. I mean, I said it here below, but this notation works for links as well. Okay, you don't need to restrict to knots. Okay, and then I use this, for example, as a interface to compute volume of links. Okay, I don't know, maybe you can get also some of the other hyperbolic invariants from here, but for me it was enough to compute volume. So so anyway, one of the advantages that's obvious for the Millett-Ewing notation that it also works for links. So you do not need one component. I must say, Hauspeth-Isseltweit notation does have now some extensions to link as well, but I do not find them very easy to work with. So mostly for knot diagrams, I try using Hauspeth-Isseltweit, and for links, I try using the Millett-Ewing notation. Okay, and another remark is there is this thing called PD notation. I do not know exactly who invented this, but so for example, in Chuck Livingston's knot info, this is used a lot. Okay, and this is then this was then, so there are programs by Oswald Szabo etc. to calculate knot flow homology from that. And so mostly the thing was, for what I used the Oswald Szabo programs, is calculating the tau invariant. So this is okay. And they use this notation. Okay, so they use this notation, this PD notation. But what I want to emphasize is this PD notation is in fact only kind of a poor man's reinvention of the Millett-Ewing notation. So what the PD notation is basically, it's like the Millett-Ewing notation, except that you restrict to a knot, and then you kind of label the crossings consecutively along how you run along the curve or something like this. So, in order to be able to do this kind of computation, I wrote myself, it is very easy to, I mean, to convert from here to here. So when I have the Millett-Ewing notation for a knot, okay, so for a knot, I can very easily convert it. So this is, I mean, GW. I wrote myself a GWK script. Okay, but it's not difficult to do that. And then, so obviously this means I cannot. So when I'm here, then I can go to Millett-Ewing, and then I can do this, and then I can compute the tau invariant, for example. Okay, so kind of this Millett-Ewing notation is very versatile and stands in the center of a lot of useful stuff that you can do to compute. So invariance and whatever. Okay, I must say that there are some other features here, for example, homomorphisms. So like homomorphisms of the knot group, etc. For this, so these tools of Knotscape work directly with Taucat-Fisseltwert, and I don't know how to make this work with Millett-Ewing. Okay, but there are many things that you compute using the Millett-Ewing notation, at least implicitly, so at least being temporarily generated. So okay, so this means Millett-Ewing notation is rather useful. So now I explain what the notation does. Okay, so this was enough of motivation. Now you see that there is some use for the Millett-Ewing notation. So let's make an example. So how does the notation work? Okay, and I start again with my favorite example, which I also drew last time. So this is a treadmill. And let's say, and I should say this is right hand. So this means that the crossings are positive. And this is important. So I said in the Taucat-Fisseltwert notation, it doesn't really matter how you mirror the diagram, but for Millett-Ewing, it matters a lot. Okay. So, and the notation, how it is generated by this is, so you get the following. So first stands an integer with a dot, and this is the number of crossings. So there are some spaces here, which there should be some spaces. And then here comes another integer, let's say 1, which is an identifier. And as in Knotscape, I explain what is the meaning of this identifier. So this is essentially an integer that you provide with the notation in order to encode some information that is useful to carry along with it. So, for example, it can be the order of the knot in a table. Okay, but it can be be also the order in which some program generates diagrams. Okay, so it is just an integer that is provided in order kind of to distinguish between, if you have many diagrams, to understand which diagram is which, because when you see the notation of the thing, you do not really see what it is. So this is the first line. And then you do the following. So you number the crossings in some way, let's say 1, 2, 3. Okay. So, and there are two situations. So this is the skin sign that I explained last time. So this is plus and this is minus. So I reminded this is called the skin sign. Okay. And in either case, there are 4 ends of the crossing. And they can be distinguished by saying it is the upper strand and is the lower strand, and it is the incoming strand on the outgoing strand, because you have an orientation. So I emphasize this is notation for oriented diagrams. Okay, so this means, so this is upper outgoing. Okay, so and this is, for example, lower income. Okay, so it is below and it comes in. So the arrow is at the other end. So this when there's no arrow, this means it goes in, and when the arrow is out is at the end, and it goes out. So you have upper and lower incoming and outgoing. And what one needs is you assign a letter A, B, C, D to these 4 ends, so that the upper outgoing is always A. So this is upper outgoing is A, and here's the upper outgoing is A. And then in clockwise, you label the others B, C, D. So this is okay. So you have now an end of a crossing is specified by 2 things: the number of the crossing and the letter A, B, C, D, which indicates which of the 4 ends of the crossing you mean. Okay. So and now, so this means in this, if we do this here now, let's see, I didn't draw it big enough. Let me maybe draw it bigger because it will mess it up. This is one, let's see, I'll say 1, 2, 3. And now this is A, B, C, D. And this is also A, B, C, D. So you must keep in mind that the orientation is always this way. So, and then this is also A, B, C. So, and now what you do here is you write for each crossing how the four ends of the crossings are connected to other crossing ends. So here comes crossing number 1. Okay, so the notation is you write the number of the crossing and you write it consecutively. So in each line there is one number 1, 2 until the number of crossings. So 1, 2, 3. Okay. So there is an integer. Then follows the skein sign, which is plus or minus. In this case, all the crossings are plus. Okay. And then comes, so after the skein sign comes a sequence of 4 combinations of integer and letter A, B, C, D, which explain how the 4 ends of crossing 1 are connected. So end connected to 1A and connected to 1B, 1C, and 1D. So now let us check this out. So what is 1A connected to? So this is connected to 3B. Okay, so this is 3B. Then what is 1B connected to? 1B is connected to 2A. 1C is connected to 2D. And 1D is connected to 3C. So what happens with 2? So 2A is connected to 1B. 2B is connected to 3A. 2C is connected to 3D. And 2D is connected to 1C. And finally for 3, so 3A is connected to 2B. 3B is connected to 1A. 3C is connected to 1D. And 3D is connected to 2C. Okay. So, and what you will see, so what you get, what this program will render you, it will render you this text. And in the article that I have uploaded, you can find also the example for figure right now. I do not want to do this. Okay, so this is how annotation it looks like, and then usually at the end there is an empty line. So here is usually an empty line. And then you can have more. Okay, so you can of course stack these notations for more diagrams. And this is what the Millett-Ewing program works with. Okay, so the Millett-Ewing programs then compute these polynomials from that notation. So now, warning and historical remark. So these polynomials, they were invented around, so let's say late 80s. Okay, so this means, so this is now about almost 40 years ago. And the Millett-Ewing program was written around that time. So you can see the article that I have uploaded you was from 1991, but I mean, the program was a couple of years earlier. So, and at that time, I mean, you do not know, so you have not been alive at that time, but you didn't know how computer looked in the 1980s, okay? So, and how programming looked like. So what they were trying to optimize this, since the computers were very slow, so that they can compute as much as possible. And so yeah, I mean, I forgot to say, so Millett, okay, Mr. Millett, okay, is the M here, okay, so this is also, he's also one of the co-discoverers of that polynomial. So anyway, so the Millett-Ewing programs were meant to be very fast, because they run on extremely limited hardware, okay? I mean, you do not know how computers look like at the time. So, and in order to be that fast, they were trying really to optimize wherever they only could. And this resulted in code which is extremely difficult to maintain. Okay, and it then, when you started then moving it to more modern computers, it started creating errors. Okay, so in particular, I think I've said this before, but when Thistlethwaite upgraded the Millett-Ewing programs to work for Knotscape, all these problems that were in the Millett-Ewing programs, they of course were inherited into Knotscape. So this is the reason why, I mean, at least for me, in many cases when I try some more complicated diagrams or something, then the programs don't work. Okay, so the program crashes. So these programs were fast, but they are very difficult to maintain, and they're very difficult to port to more modern computers, okay? So I have tried for a very long time to make these programs practically workable, but unfortunately, it is too difficult, I mean, to fix them, especially the one for the Kaufman polynomial. So, so this program, some version of it I'm still using for low crossing diagrams because this works more or less, but the one for the Kaufman polynomial is even more difficult. So for example, in the last installation that I made on my computer of Knotscape, it was not working even for 12 crossings. So I got, it was crashing. And so so the program has a lot of errors. And you can have errors on every possible level. So what are possible errors? I mean, I do not like talking about errors too much, but in order to make the warning explicit. So the first thing that you can do is you can have a, okay, so it can crash. Okay, and then of course, when it crashes, then you know that something went wrong. So the program can crash. But unfortunately, there are other things. So it can give you an infinite loop. So the program runs into a loop and never exits. And the only reason that I knew that this happens is that the program have some status file that it is updated, and this status file update fails at some point. I mean, it stops. So you can assume that this ran into a loop. So this can happen. So then you can have obviously wrong outputs. I mean, this is so you simply look, so it gives you a polynomial, and then you look and you immediately see that it cannot be true. So for example, you know that if you have a knot, then the powers of the powers of these variables v and z, okay, I mean they're called differently here, but it's equivalent, must be even. So you input a knot, and then you see that you get some odd power of the variable. So and then you obviously see that it is wrong. So it's useless. But the worst of all this was when you get hiddenly wrong out. Okay, and hiddenly means, I mean, with this, something which looks to be right, okay, but it is still, there's still something wrong with it, but it's not easy to see. So for example, I was computing, so I was using in some older, like, I don't know, 10 years ago, I was trying to compute two cables of mutants. Okay, so then you don't need to know what exactly this means, but the theory says that the Kaufman polynomial of these two knots must be equal. Okay, and then I compute this. This has, I don't know, 60 crossings or something, so it takes 3 days per knot, something like that. And then I compare the two things and I see that they are different, but they're different only so you have some huge area of coefficients. So let's say this is A and this is Z. So Kaufman has two variables A and Z. Okay, so you get some, when a knot gets complicated, then these polynomials become huge and they have many coefficients. Okay, and now I compare them and then I see that they are mostly okay, but somewhere here in the middle, okay, there are many, one or two coefficients are different. So even this is possible. So you can have, and now you know that they must be equal, so one of them is wrong. Okay, and now I have tricks to check which of them is wrong. And so I mean, to distinguish now which is the right one, which is the wrong one. I have tricks for that as well, but okay, now this becomes a longer discussion. But by any means, the upshot of that is that now, okay, now these things are unfortunately unreliable. Okay. So if they run, as I said, if they run, particularly because computers now develop in Gaussian fashion, so if they run extremely fast. And if they produce a result. But unfortunately, they produce many errors, and which are also sometimes difficult to notice. Okay. And so what is the solution? Okay, the solution to this is basically that I started redoing the whole project by myself of implementing this. So I replace, so I wrote my own products for P and F. So for P and F based on the Millett-Ewing notation. Okay. And I was trying to kind of imitate more or less what Millett-Ewing were doing. So maybe let me just try to give some kind of upshot of the algorithm that they use. And this is the reason why I wanted to keep this here. So this is, I mean, to those who do not know, so this is a relation. Okay, this is sometimes called the skein relation. Okay. And this relation can be used to recursively compute the polynomial, because if you do this properly, okay, you can relate the polynomial of one link diagram to two other link diagrams, but they are simpler. And then you can work recursively until basically you get down to, so you have some diagram, and then say d minus d0, and then you continue doing this binary until at the bottom you reach diagrams that have no crossings. Okay, so diagrams with no crossing, these are unlinked diagrams. So diagrams that look like that. Yeah, maybe it's important remark, because before I forget. So you see this notation captures many things. So it is sensitive, for example, if you reverse orientation of the whole diagram. It is sensitive if you reverse the orientation of individual components, because the sign of crossing changes, and then the number of the ends changes, and then how the ends connected changes. So this notation is very sensitive with regard to changing orientation. Similarly, with regard to mirroring. You can very easily see that when you mirror a diagram, the notation changes completely. So this is why it is much, it is kind of safer to work with it, especially for links, than with the Dowker-Thistlepath notation. So, but there's one thing that this notation does not capture, okay, and this is the crossingless loop. So if you have some diagram, okay, so for which you have a notation, and then you add an extra loop at the end, then the notation has no means to capture this loop, because there are no crossings on the loop. So when it's a crossingless loop, then there is no crossing loop that says what is connected to what. And this is something that has to be carried along. Okay, so what the Millett-Ewing algorithm does is it tries to apply this skin relation along what is now called the skin tree. Okay, so you relate the polynomial of a diagram to simpler, okay, these are simpler diagrams, and you continue doing this properly until you end up with unlinks. And so these are terminal nodes. Okay. And now it uses slightly also some more complicated transformations, etc. But this is kind of the idea is that you can use this relation to break down the polynomial of this into something, and then you just have to add them. Okay, and so it uses skin tree. Okay. This is one thing that it does, and then it also has a restart facility. So what does restart mean? Restart means you try to do this on some diagrams that have very many crossings, and then it takes a very long time, and then you cannot be certain that this will run smoothly until the end. So something can happen, like, for example, you can have power failure or whatever, or some computer crash or whatever. Okay, and then it is useful to save intermediate steps. Okay, so to save how long the program advanced. And the Millett-Ewing program has this facility, so you can make the program write a dump of its internal state, and then you can resume it from there. So then you don't have to start from the beginning. And my program does the same, okay? Except that, and then I have added more things. So my restart file, for example, is a text file, unlike Millett-Ewing. So I tried, of course, not only to redo everything, but to do it better. So I can restart, and then I can do also more things, but I think that's now, okay, I have said enough to fill a whole lecture, so maybe the next time I can talk about, or at some other occasion, I can talk about how I further develop this.